like to do some calculations involving half-life. And what we know about nuclear decay is that it's a first order process, so it's bound by the equations that we talked about when we were talking about first order reactions. What I'm going to focus in on here is the integrated rate law, which came from this rate expression here. So let me show you how that relates to half-life. So what we can do is we've got our integrated rate law, and what I can do is take the log of A, subtract log of A0, and that equals negative KT. And that's the same as when we've got a log, we can just divide them if we're subtracting. Alright, so that's what we've got. Now A here is the particles at time t. So the number of particles at time t, if you like. And A0 is the initial number of particles present. So what that means is that A over A0 is equal to the fraction of particles remaining at time t. And the key word there is remaining. Not lost, it's remaining. It's whatever's left at that time. It's fraction of particles remaining at time t. Alright, so we can apply that now to these kinds of problems. We also know what the half-life of a first order process is, and that's 0.693 over K. And we can get that by taking this and substituting in T equals T half, and then for A we substitute in A0 over 2. That's what half-life is. Half-life is the time it takes to get to half of what you originally started with. A0 is what you originally started with. A0 over 2 will be where it is at the halfway point, with the halfway point, and then the time will be the half-life. So once you sort that out, T half equals log 2 over K. Alright, so now we've got two equations that we're going to work with here, these two here, and that will allow us to figure out the time it takes to get to a certain point. So here's an example. Calculate the time required for 95.00% of a sample of 240 plutonium to decay, and I'm giving you the half-life here. Now the important words here are to decay. Alright, so what I do, I first of all find out the value of K. That's going to be the essentially the rate constant. Now I've got the half-life here, so I can figure out K by log 2 over T half. That gives me this 1.05 times 10 to the negative 4, and the unit on that is years to the minus 1. That's because years were on the bottom here. So it's per year is the other way of stating that. Now remember that the A0 the A over A0 we talked about earlier is a fraction of particles remaining at time equals t. And the question is asking how to find the time it takes for 95.00% to decay. So for 95.00% to be gone. So if 95.00% has decayed, there must be 5.00% remaining. That can be converted into a fraction because it's 5.00 over 100, so that's 0.0500, and that's what gets subbed in for A over A0. So we sub that in for A over A0, and we put it over the K value we calculated earlier, and we get this figure, 28,500 years. And if you look at that, it makes sense. 6,580 years is the time it's going to take for half of the plutonium to decay. So if it's 95% is going to decay, you're going to expect it to be certainly more than 6,580 years. Alright, so what about if we change the wording slightly and we make it 95% of the sample of plutonium to remain? So different wording here. It was decay last time, now it's remain. So we go ahead, we do the same thing, calculate K. If 95.00% remains, then that is A over A0, which is the fraction remaining. And we convert that into a fraction, 0.9500, and we get 489 years, which makes sense, because that would mean it doesn't take that long for 5% to decay to 95% left over. So 489 years seems reasonable, especially given that the half-life is 6,580.